We're going to take a look at factoring when I have special cases or special circumstances for my trinomials. Now, we know that trinomial means I should have 3 terms, but for a problem like this, I only have 2. It looks like my middle term, my x term, is gone. In cases like this, that means that b is equal to 0. So what I actually have is x squared plus 0x minus 4. So we're going to look at how to factor something like this. So if we take a look at example 8, I'm going to factor 9r squared minus 4. And we'll use the AC method here. So I'm first going to rewrite this with that middle term showing as our reminder that our b is 0. Look for a GCF here. We don't have one, so I'm going to go ahead and move on to multiplying my a value and my c value. So a times c would be 9 times negative 4, which is negative 36. Now we want factors of negative 36 that would add to 0. So what we're looking for is factors of 36 that are actually the same number, but one positive and one negative, so that when I add them together I get 0. So we're looking at 6 times negative 6. The same absolute value of our number, we could say, but with opposite signs, so that when I add those numbers together, they reduce each other out, they cancel each other out, and we end up with 0. So we would have 9r squared, remember AC method, we replace this middle term by splitting it up, plus 6r minus 6r minus 4. And then we factor by grouping, so split our problem up into our 2 groups here. My GCF for this first group would be 3r. That would leave me with 3r plus 2. For the second group, my GCF would be 2 is a GCF for 6 and 4, and since they're both negative, I'm going to pull out a negative 2, and that would leave me with 3r plus 2. My stuff in parentheses is the same, which should always be the case when I factor by grouping. So now that stuff in parentheses is my GCF to pull out, and that leaves me with 3r minus 2. So there would be my factored form. We can take the same approach using the slide method. So if I were to rewrite this, that would be x squared plus 0x minus 81. No GCF here, so I'm going to multiply a and c. A is 1, multiplied by c, which is negative 81, and I'm looking for factors of negative 81 that add to 0. So again, I want something that's the same number with opposite signs. That would be 9 times negative 9 for this problem. So if I'm using the slide method, I'm going to go straight into my factors. X plus 9, x minus 9, and then we would divide by our leading coefficient. That's just 1 in this case, so my final form is going to look the same as what we had here. X plus 9 times x minus 9. Okay, and I can continue that same pattern. So if I'm looking for numbers for number 10, for example, where I have my leading coefficient here of 1, I have no AB term, so I could rewrite this as a squared plus 0ab minus 16b squared. I would be looking at multiply a by c. That would give me negative 16b squared. And I'm looking for factors of negative 16b squared, factors of this goofy term that would add to 0. Same idea. I want a thing times itself where one's going to be positive and one's going to be negative. So that would be 4b times negative 4b. And I could factor even something that looks kind of weird with all these strange variables in here. So this would become a plus 4b times a minus 4b. And for slide method, I would divide by 1, but again, that's going to give me just this. So when our b term is 0, notice that in each case, the term at the front of our factors was the square root of our first term, and the term at the back of our factors was the square root of our second term. X is the square root of x squared, 9 is the square root of 81. A is the square root of a squared. 4b would be the square root of 16b squared. So our special pattern here that we can use to our advantage is that when I have something that looks like ax squared minus c squared, right? When I have just that x squared term and my constant term, that's going to factor into the square root of my first term at the front of each factor, and the square root of my c term at the back of each factor. And then also notice that the signs are opposite in each of these factors. So we're actually factoring into conjugates. So I'll have the same numbers here, but with opposite signs in between.